In this screencast, we're going to talk about the third and final aqueous phase reaction, known affectionately as redox. And it's called redox because, and it's all capitalized because it's actually a machination of two different words, oxidation and reduction. So, redox reactions are aqueous phase reactions, generally aqueous phase reactions. They can happen in other things that involve a change in oxidation state. Now, what the heck is an oxidation state? This is going to sound more confusing than it really is, but the textbook definition of oxidation state is the fictitious charge on an atom or molecule, in the molecule, or the actual charge of an aqueous ion. So, for example, all of our aqueous ions that we've talked about so far in this section, so we talk about a sodium plus 1 ion. The charge of that sodium plus 1 ion is the actual oxidation state, the actual charge on the aqueous ion. The fictitious charge on the atom in a molecule, you can think about that as like when we were thinking about molecules and their charges when we were making neutral species like aluminum oxide, Al2O3. We said that the aluminum was a +3 and the oxygen was a -2. Those are the oxidation states. You know them. You have faith that you'll remember what they are. So, oxidation states, metals can either have a zero oxidation state when they are neutral and by themselves, or it can be positive. So, we already know this, that metals can only have +1, be positive ions. That means they can only have positive oxidation states. Again, oxidation state is the actual charge on aqueous ions. Unless it's a pure solid, then the metal has an oxidation state of 0. Group A metals, the oxidation state is equal to the group number. That's why we say that sodium is always a +1 ion and that calcium is always a +2 ion. You know that calcium can only either have an oxidation state of 0 if it's a pure solid or a +2 if it's an ion. B metals, the oxidation state varies. You know that because we call iron 3 chloride iron 3 chloride. Iron 3 is the charge of the iron. That's why we call it iron 3. That means that the oxidation state of the iron in that case is, you guessed it, +3. Iron 3 +3. That's not a coincidence. That's why we call it that. Nonmetals are usually less than 0 and are predictable. Now, this whole argument we've talked about when we talked about naming molecules. We said that, okay, so fluoride, chloride, bromide, those are always -1 ions. We know they're -1 ions because if they gain 1 electron, they become noble gas-like. Oxygen and sulfur like to be a -2 because if they gain 2 electrons, they're like a noble gas. All that stuff we've covered before. So, fluorine, or fluoride ion, -1 ion, the actual charge is -1. So the oxidation state of fluorine, of a fluoride ion, is -1. The oxidation state of sodium fluoride, NaF, the oxidation state of the fluoride, or the fluorine, is -1 in both cases. Pure elements, by themselves, the way Mother Nature made them, not as ions, all have 0 oxidation states. So O2 gas, the oxygen has a 0 oxidation state. Iron solid has a 0 oxidation state. O2 liquid has a 0 oxidation state. If you're by yourself, and you're a solid or a gas or liquid or whatever, you're the pure substance, then you have a 0 oxidation state. So we have two different processes. The reason we call these redox reactions is because it's oxidation and reduction. The reason we smash them together, we don't sit here and talk about, okay, let's talk about oxidation reactions, and oh no, let's talk about reduction reactions. The reason why we tie them together and we lump them together as redox reactions is because they have to happen at the same time. And the reason is because in one case, we're losing electrons. And the other case, we're gaining electrons. So oxidation, by definition, is in some reaction, some species loses an electron, or 2 or 3, loses some number of electrons. If you lose electrons, your oxidation state goes up. Because remember, oxidation state is sort of your charge. It's the relationship between your number of electrons and your number of protons. If you lose electrons, the oxidation state goes up. In reduction, it's, by definition, in some reaction, a species gains electrons. And in that case, if you gain electrons, your total negative charge goes, your negative charge goes up, and so sure enough, your oxidation state will drop. So again, these are tied together. Reduction always happens with oxidation because you can't have free electrons sort of running around by themselves. It's just not against, it's totally against the rules. You can't just sort of have something say, yeah, I lost 3 electrons, and have those electrons hang around on the street, and then 10 minutes later some other element comes and picks up those electrons. It doesn't happen. The electrons always must be in possession of somebody. They're like $1 billion bill or $1 million bill. You don't just find them lying on the street saying, oh yeah, I owe my buddy $1 million and I have this $1 million bill, so I'm just going to leave it on the sidewalk and he'll come by in about 10 minutes and pick it up. Nope. That $1 million bill, someone's holding it, someone possesses it at all times. Oxidation and reduction happen at the same time. That's not a way of thinking about it. Because the electrons have to go from one species to another. They always have to be in the possession of somebody. But they can be transferred easily. Electrons are small, they're light, easily removed. So let's consider hydrogen, oxygen reacting to form water gas. So here's hydrogen, it's a pure element in its gaseous state. So the oxidation state of this oxygen is 0. This hydrogen is 0. Here's O2 gas, pure gas. Oxygen's by itself. The oxygen has an oxidation state of 0. But over here in my molecule, now I have a molecule, and so again, the oxidation state is sort of the fictitious charge of the species in the molecule, but you know, the charge that we use way back when we were like making these molecules. So there's hydrogen ion. The hydrogen is a +1 charge, and since there's 2 of them, it gives a net +2, and my oxygen has a -2 charge. So you'll notice the hydrogen goes from a 0 to a +1 charge. So the hydrogen went from 0 to a +1 oxidation state. Its oxidation state went up. That was oxidation. It lost electrons. It went from 0 to net +1, so it lost 1 electron. And the oxygen, you'll notice that the oxygen went from a 0 to a -2, so it gained 2 electrons. Now obviously the number of electrons has to be the same. The number of electrons lost needs to be equal to the number of electrons gained. That whole electrons have, have to be held on by somebody, so you can have like extra electrons. But that's okay because notice we have 2 hydrogens, each going from 0 to a +1, so sort of a net loss of 2 electrons. And my 1 oxygen, now granted this isn't a balanced chemical equation, so let's just put a little, pretend there's a 1/2 there. The 1 oxygen gains those 2 electrons and becomes a neutral water. Or the oxygen gains those 2 electrons. So it's 2 electrons, 1 from each of 1 hydrogen was gained by the 1 oxygen. An easy way to remember this sort of scheme, or the definition of oxidation reduction, is this simple mnemonic. Leo the lion says grr. Loss of electrons is oxidation. Gain of electrons is reduction. That's one way of memorizing it. If that's too much for you, you can remember the phrase oil rig. Oxidation is loss, reduction is gain. Because you're going to need to be able to look at a reaction and identify who's being reduced, who's being oxidized. So let us consider this simple redox reaction. We know we have pure zinc solid on the left-hand side. So its oxidation state is 0. And we have zinc over here as a +2 ion. So the zinc lost 2 electrons. On the left-hand side, we have copper with a +2 charge, and over here, it's got a neutral charge. So it gained 2 electrons. So the zinc solid is being oxidized. Zinc solid is being oxidized because its oxidation state is going from 0 to +2. And the copper ion is being reduced. It's going from a +2 to a 0. Now I can't say zinc is being oxidized and copper is being reduced because I have 2 different zincs. I have a zinc over here, I have a zinc over here, and they are very different. I have a copper over here, I have a copper over here, they are very different. So I have to be very, very crystal clear. Hint, hint, quiz question. You have to be crystal clear is when you're asking who's being oxidized, who's being reduced, you have to say exactly who is being oxidized. Well, in this case, solid zinc is being oxidized and copper ion +2 ion is being reduced. We also have another name for these. two species in that zinc solid is what is known as the reducing agent. The easiest way to sort of remember this concept is to think of a travel agent. Okay, a travel agent is someone who does all the work for you to allow you to travel, but they're sort of your agent. So we call zinc a reducing agent because by it doing what it wants to do, be oxidized, it is allowing somebody else, agent, to be reduced, right? So being oxidized, taking or losing those two electrons is allowing somebody else to be reduced. Somebody else, your agent, to be reduced. And of course, the copper ion is sometimes referred, in this case, it can be referred to as the oxidizing agent, because it is being an agent, and it doing something, in this case being reduced, allows somebody else to be oxidized. So it's the oxidizing agent. Whoever's being oxidized is the reducing agent. Whoever's being reduced is the oxidizing agent. It's one big vicious circle. So in the real world, redox reactions are important for lots of cleaning agents are used for sort of oxidizing stains and nasty stuff that you spill, allowing it to turn solids into ions that allow them to be washed away easily. It is also that very, very important chemical process known as photosynthesis that is very much a redox reaction, and also a lot of body chemistry, so fat and sugar conversion. Those are all redox reactions. They're very complex, they give a lot of energy, and they're really, really freaky important to keep you and every other animal and plant on the planet alive. One more, or a couple more notes about redox reactions is when you're balancing chemical equations, you got to be very, very careful in terms of balancing. We look at this reaction and we think the reaction's balanced because say, oh look, there's one ion over there, there's one ion over there, there's two chlorines over there, there's two chlorines over there. But it's not. Back when we were balancing chemical equations, we were only looking at the number of atoms. The oxidation, if you go back and look at all of those reactions, the oxidation states of everybody didn't change. Another way of looking at this is that this equation is balanced based on molecular, on the number of atoms, or the number of protons, if you will, but not for the number of electrons. Because if you look, the total charge on the left-hand side, well, that's oxidation state of 0, oxidation state of 0. The total oxidation state on the right-hand side is +3 and -2. 2 times -1 is -2. So I lost an electron somewhere. I have a net +1 charge on the right-hand side and a net 0 charge on the left-hand side. Well, that can't happen. I have to balance the electrons. So we can do that easy. If we think about it a little bit, we have to have actually more of the irons. And now, if the irons are still balanced. We just put a 2 and a 2. So now we have a net +6 charge on the right-hand side, and I have 3 chlorines, 3 chlorine molecules. So that's 6 chlorines on the left. I have 6 chlorines on the right. So the number of chlorine atoms is the same, and now the charges are balanced. All this basically means is when you're talking about redox reactions and the charges are changing, you have to be careful about looking at the number of electrons. Good luck.